So in this problem, first of all, we want to show that some vector field, a two-dimensional vector field, is conservative. If they're asking you, is this conservative, without the second part, they want me to find a potential function, if so. So I might as well just get started with trying to find the potential function. But if they're just asking, is this conservative, you can do the curl of this thing in 3D or do the partial derivatives to see if this actually works. So if I think as f as p comma q, and I compute the derivative with respect to of q with respect to x minus the derivative of p with respect to y, this should be 0 if and only if is conservative. If and only if you think of that as a three-dimensional vector field, that will also be conservative if the curl of f is 0, which amounts to the same calculation of derivatives. So let's just double check what's happening here in terms of derivatives. So what is the derivative with respect to x of q? Q is here, and the derivative with respect to x is the derivative of x cosine xy, the derivative of x times cosine xy plus x times the derivative of cosine xy. So it's actually minus. So we get that, and if I take the derivative of p with respect to y, then I get the derivative of y times cosine xy minus the derivative of cosine xy, which there will be an x here, sine of xy. And you see that these are actually exactly the same function. So yes, it is conservative. So now I can move on to try to find the potential function. So 1, 2, how do I find a potential function? So a potential function is a function f such that the derivative or the gradient of f, of little f, is capital F. So what that means is that the derivative of f with respect to x is that function p, the first coordinate, and the derivative with respect to y is that second function q. So what we do usually is take one of the two and integrate, either do the integral of p with respect to x or of q with respect to y. Y seems more difficult to integrate, so I'm going to do x. I'm going to do p. So I find the integral of y cosine xy with respect to x. What's the integral of y cosine of xy with respect to x?
Sine xy plus c.
Sine xy, did you say plus c?
Or plus a function of y.
Plus a function of y. So it is a constant, but that constant can depend on y. Yeah. So you have to, just so you don't forget that this is not just a number, that is a function of y, you should call it something and say with parentheses y, so to remind you that that can depend on y. If you don't see like how to do this, you can just do a u substitution. If you substitute u equals xy, then du with respect to x, this is just y dy, and then you see that that integral is going to come out nicely with a u substitution. Okay, so now that I have my candidate for f, I have to try to figure out what is this constant with respect to y. So now we take the derivative with respect to y. So I'm going to now take the derivative with respect to y again and see what I get. With respect to y, I get x cosine of xy plus whatever the derivative of this function is with respect to y, right? And this should match whatever this other function was, so this should be x cosine of xy plus 2y. So whatever this function is, its derivative is 2y, so now I can integrate with respect to y and see that it should be y squared. The constant function should be y squared. Yes. Yeah. If what you're asking is, I have to find, is this a gradient? If you can spot it, if you can figure it out that I think the function is this, because this function, I can sort of figure out that what it might be. So if you can spot it and say, like, I think the potential is this, and I'm going to check that it works, then you're all set. You are doing integrals in your head, right? To find out what it is, you're sort of like reversing derivatives in your head. So you are doing what I'm doing by hand, which in some cases, if you're stuck and you don't see what could be the potential function, this is what you would do. But yeah, if you figure it out, then you're okay. So what I think my candidate is the sine of xy, and then the constant function should be y squared. So let's see if that works. If I take the derivative with respect to x, I will get y cosine y and 0. So I get this. And if I take the derivative with respect to y of this, I will get x cosine xy plus 2y. So this one works, or this one plus any number works. Yes, correct. Yeah, I wanted to show you that you could do this just to check that something is conservative without having to find the potential. Taking derivatives is very easy. So there could be some function, some vector field that is very difficult to find what is the potential, that I can at least check that, yes, it is conservative without doing any work. Why am I saying so? Because the last part is to evaluate an integral. And so I guess we are going to need the potential to do the integral. If this integral was a path that was a closed path, once I know that it's conservative, then if it's a closed path, I could have said, then the integral is 0, and that's it, without having to compute the potential. This path is not closed, though, so we're going to need the actual potential function. So remember that the fundamental theorem of line integrals tells me that if I am doing a line integral of a gradient, that is, and C goes from P to Q, then this is f at Q minus f at P. This is the fundamental theorem of line integrals. Okay? And so now we are trying to do an integral over a path of f dr, but we have figured out that this is the integral over a path. The path goes from, it went from 0, 0 to 1 pi. So it's a line, okay? Let's say it's a path that is a line. I could have parameterized that and do my line integral like we know, but this f is the gradient of the function we just figured out is the function sine of xy plus y squared dr. So it has to be this function evaluated at 1 pi minus the function evaluated at 0, 0. And this function evaluated at 1 pi is the sine of pi plus pi squared minus the sine of 0 minus 0 squared. the sine of pi is 0, so this is just pi squared. Yes, the statement said. It said used to evaluate from 0, 0 to 1 pi. And the theorem, the fundamental theorem of line integrals tells you that the path actually doesn't matter. Okay, that no matter what path I take, the integral will be the same as long as it's some like relatively smooth path. I'm sorry. I shouldn't have called P and Q. You're right. These points should be is going from A to B. Yeah. So the question is, if I have a vector field that has a z coordinate, then how do I find a potential function? The potential function, you would go in the same way. You would take the first coordinate, that is supposed to be the derivative of whatever little f is with respect to x. So I take that one and take the derivative with respect to x, and I get this, except that if this is a function of the three variables, this constant could have been a function of y and z. So what you do then is you take this one, take the derivative with respect to y, and now with respect to y, this function will have some derivative, and this function is now some derivative with respect to y, a partial with respect to y of a function in y and z. So now you take whatever is in here and take the integral with respect to y, and you get a new function that is in y and z, and then take the derivative with respect to z of that one, and that one has to match the third coordinate here. So it's sort of like this, except that there are three steps, and you integrate, take the derivative, integrate, take the derivative, and then there's one last integral actually that you have to do to figure out what is the last constant function you get is just with respect to z. In that one, you take the derivative, integrate, and then you figure out what is the total function. Okay, so we're going to find a line integral of a line integral of a curve at an intersection. So let's figure out what that curve looks like. There is again a cylinder happening here. The cylinder has radius 1. And then we have a plane, z equals 1 minus y. I can draw that line in the yz plane at 0. It looks like this. So if I continue that and grab the plane like that, what is going to happen is that I have I think I get something like this for my curve. Okay, the intersection of the plane and the cylinder will be a conic. It will be some sort of ellipse like this. How do I find a parameterization of this? What I do is drop this to the xy plane, see what the cross section is there, and then use the curve for the z value, use the plane for the z value. So what I mean is that I can parameterize such a curve in the xy plane. The projection in the xy plane will be the circle of radius 1, and the z value will be 1 minus y. Okay, so the curve looks like this. So now I can parameterize this as I can do this in polar coordinates as r, I know what the radius is. The radius is 1, so cosine t, sine t, and then the z value is 1 minus sine of t. Okay? So that is the parameterization that they're asking me for. Now I have to find the derivative, which is the vectors, the tangent vectors. Those are minus sine t, cosine t, and then just minus cosine t. That will be the tangent vector. I have to figure out also what is f evaluated are RT, because remember that the integral will be, the integral that I want eventually is f of RT dot product with r prime t dt. This parameterization, by the way, I need some values. I have to do one whole lap. So it's going between 0 and 2 pi, so this will be between 0 and 2 pi. So what is f evaluated at RT? The vector field is given here. So the vector field is minus y, so minus sine t. X is cosine t, and then z is 1 minus sine t. That is f of RT. And now I have to do the dot product with r prime t. What that's going to give me is minus sine t times minus sine t. That's sine the square of t plus cosine the square of t plus 1 minus sine of t times minus cosine t. So there's going to be a minus here. Is minus cosine t. Okay, so this is 1, because sine squared plus cosine square of t is 1, minus cosine of t plus sine of t cosine t. So that is a function that I'm integrating with respect to t. So the integral that they're asking me to do, the integral of this f dr turns out to be the integral from 0 to 2 pi of 1 minus, minus cosine t plus sine t cosine t dt. Is this going to be 0? Can I check that this is 0 without having to do much of this? This is an integral. It's a line integral in a closed loop, so I could try to use Stokes just to make sure that I'm not doing all of this when I could have just used Stokes and say this is 0. So let's just quickly, so the vector field was minus yx z, and if you do the curl of f, what do you get? I, j, k minus y, x, z, and derivatives. Derivative with respect to x, derivative with respect to y, with respect to z of minus y, x, z. The curl here is going to be the derivative with respect to y is 0i minus, in j I get 0j plus, and in k I get the derivative of x plus the derivative of y. I actually get 2k. Okay, so it is not 0. It's constant. So it is 0, 0, 2. That's the curl, but it's not the 0 vector. So this is not going to be a 0 integral, not necessarily because of the vector field being conservative. Okay, so you can do that integral, and that integral at the end you get 2 pi if you compute that. By the way, the integral of cosine t that we know, the integral of sine t cosine t, you can take this sine t to be the derivative of cosine t. So if you do a u substitution for cosine t being u, then this also is not hard to do. And the answer is 2 pi. All right, so I think I'll stop here.